What you're about to watch is something a little different, something more interactive than anything I've made before. And that's because the visuals were largely done not by me, but by Ben Eder, who runs an excellent computer engineering channel that you should all check out. All of the web development that made this project possible is completely thanks to him. So, to set the stage, last video I described Quaternions, a certain four-dimensional number system that the 19th century versions of Wolverine and the Old Man from Home Alone called evil for how convoluted it seemed at the time. And perhaps you too are wondering why on earth anyone would bother with such an alien-seeming number system. Well, one of the big reasons, especially for programmers, is that they give a really nice way for describing 3D orientation, which is not susceptible to the bugs and edge cases of other methods. I mean, they're interesting mathematically for a lot of reasons, but this application for computer graphics and robotics and virtual reality and anything involving 3D orientation is probably the biggest use case for Quaternions. To take one example, a friend of mine who used to work at Apple, Andy Matuszczak, delighted in telling me about shipping code to hundreds of millions of devices that uses Quaternions to track the phone's model for how it's oriented in space. That's right, your phone almost certainly has software running somewhere inside of it that relies on Quaternions. Our goal is to understand how exactly this works, because describing 3D rotations with 4D numbers is not exactly a simple idea. But instead of doing this in a format where I just show you the visuals, we'll do it in a context where, at any point, you can pause and play with the visuals for yourself. Here, go ahead and try it. Pause the video and try playing around with the elements you see on screen. Okay, just kidding. YouTube cannot at all do that. So in a moment, I'm going to point you to a separate website where the interactive video is hosted. But before jumping into that environment to build the intuition for Quaternions, it's worth saying a few more words about the challenge of 3D rotation. The thing is, there are other ways to think about computing rotations, many of which are way simpler to think about than Quaternions. For example, any of you familiar with linear algebra will know that 3x3 matrices can really nicely describe 3D transformations. And a common way that many programmers think about constructing a rotation matrix for a desired orientation is to imagine rotating an object around three easy-to-think-about axes, where the relevant angles for these rotations are commonly called Euler angles. And this mostly works, but one big problem is that it's vulnerable to something called gimbal lock, where when two of your axes of rotation get lined up, you lose a degree of freedom. And it can also cause difficulties and ambiguities when trying to interpolate between two separate orientations. If you're curious for more of the details, there are many great sources online for learning about Euler angles and gimbal lock, and I've left links in the description to a few of them. Not only do Quaternions avoid issues like gimbal lock, they give a really seamless way to interpolate between two three-dimensional orientations, one which lacks the ambiguities of Euler angles, and which avoids the issues of numerical precision and normalization that arise in trying to interpolate between two rotation matrices. To warm up to the idea of how multiplication in some higher dimensional number system might be used to compute rotations, take a moment to remember how it is that complex numbers give a slick method for computing 2D rotations. Specifically, let's say you have some point in two-dimensional space, like 4, 1, and you want to know the new coordinates you'd get if you rotate this point 30 degrees around the origin. Complex numbers give sort of a snazzy way to do this. You take the complex number that's 30 degrees off the horizontal with magnitude 1, cosine 30 degrees plus sine of 30 degrees times I, and then you just multiply this by your point, represented as a complex number. The only rule you need to know to carry out this computation is that I squared equals -1. And then, in what might feel like a bit of black magic to those first learning it, carrying out this product from that one simple rule gives the coordinates of a new point, the point rotated 30 degrees from the original. Using Quaternions to describe 3D rotations is similar, though the look and feel is slightly different. Let's say you want to rotate some angle about some axis. You first define that axis with a unit vector, which we'll write as having I, j, and k components, normalized so that the sum of the squares of those components is 1. Similar to the case of complex numbers, you use the angle to construct a quaternion by taking cosine of that angle as the real part, plus sine of that angle times an imaginary part. Except this time, the imaginary part has 3 components, the coordinates of our axis of rotation. Well, actually, you take half of the angle, which might feel totally arbitrary, but hopefully that's going to make some sense by the end of this whole experience. Now let's say you have some 3D point, which we'll write with I, j, k components, and you want to know the coordinates that you'd get when you rotate this point by your specified angle around your specified axis. What you do is not just a single quaternion product, but a sort of quaternion sandwich, where you multiply by q from the left and the inverse of q from the right. If you know the rules for how I, j, and k multiply amongst themselves, you can carry out these two products by expanding everything out, or more realistically by having a computer do it for you. And, in what might feel like a bit of black magic, this big computation will return for you the rotated version of the point. Our goal is to break this down and visualize what's happening with each of these two products. I'll review the method for thinking about quaternion multiplication described last video, and explain why half the angle is used, and why you would multiply from the right by the inverse. On the screen right now, and at the top of the description, you'll see a link to the website Ben Eater set up with the interactive video tutorial, where you can play around with the visuals of this setup at each step of the way. See you there.